Are you gonna check yours?
You can be in your office.
Are you gonna check yours?
Yep.
After this class?
I can't after this.
I'll be straight up.
After 3 o'clock I can. I've got chemistry lab.
Oh yeah.
Mm-hmm.
Who do you have for chemistry? I love him. He is best. He is the best.
They weren't bad except for people that didn't do well.
What did you say, Doctor?
I said the tests weren't bad except for the people that didn't do well.
Everybody did good except for the people who didn't.
You really don't think you did well?
And I think on the test,
I'm never
you
confident.
look at them, it says that there was 88 points possible. I knocked it down to 80. So, 72 would have been in the A range, 64 would be in the B range, and 56 in the C range when you see the numbers.
Hoping for that C. Or above.
And then it'll be an A.
This is weird.
It's like a,
I'm very confused.
I think it tastes like.
Kind of like coconut. Like coconutty, but like also a Tootsie Roll. It's really weird.
What the heck?
I kind of like it.
I'm intrigued.
It's like caramel. It's weird. You
Multi-layered
should get
sucker.
one. You should get one.
Where are they?
In front of the library.
Alright, I might have to make some random stuff.
Make a stop. It's the one in the green wrapper.
Alright.
It's not good. At first I was like, this is disgusting. But now I really like it. So.
It's like a Sour Patch Kid kind of.
Yeah.
Or they're sour, then they're sweet.
I love those commercials.
Yeah.
I was like being mean.
I have about 2 minutes and 20 seconds of nothing. It's great.
Sweet.
Yeah, I'm just recording it.
Record him everywhere he goes.
I do. I want to make
Dr.
sure.
Preston, when would you say our exam is going to be? What day?
I don't know yet.
One of those days.
I'm trying to make sure you get 5 exams. So if we include the finalists, the last regular exam during that time frame, we need at least about 4 days to cover the lecture material before then, which we will get 3 of those the first week of December, and if we use the last week, Thanksgiving's gonna mess us up. We'll have to see us the day before or after, but in that time frame. Thanksgiving.
Okay, so-
Hopefully we can get it before.
Okay,
And
so
then that gives us enough time after to cover what we have to cover.
Thanksgiving Day.
Okay, I have a
is
question.
Off that week, right? We come
The
to school.
Friday.
Oh, we get Black Friday off too? Okay.
I have a question about the light and dark reactions. So is it similar to the anaerobic and aerobic processes in cellular respiration where it's like if there's no light and the dark reactions still continue?
If there's no light, the dark reaction still occurs.
And ATP, does ATP get made in that, or
Do what?
can
Guys,
can energy be made in that? Like, can a plant live just off
energy
of
is
that?
not made in the dark reaction.
Oh, okay.
It uses the energy made in the light reaction
To make
to
food.
go through carbon fixation to make the carbohydrates.
Yeah. Okay.
Okay,
Thank you.
this is where we left off last time. We were talking about those photosystems. You will need to know what these basic parts of these photosystems are. And I'll show you the little diagram picture here coming up in just a second. But photosystems occur, number one, remember they are in the light reaction part where the photosystems are. We've got light reaction, dark reaction. The light reaction captures energy. The dark reaction uses that energy to then make a carbohydrate in the form of that simple sugar, CH2O. Okay? And it says here that these photosystems have a thing called the reaction center. And you are going to find that's where specific chlorophyll molecules can capture energy and then pass it to a certain place. These are called the light harvesting complexes. So let's look here and just follow the bouncing green ball. Light in the form of photons hit the leaf. These are pigments. Now, if you look at these, light hits, and these are hitting they're hitting the leaf. Light goes in through the chloroplasts. Chlorophyll gets excited, picks up this energy, so that's what we're talking about. Notice it says this is in the thylakoid space, the interior of the thylakoid. Remember the thylakoid? Let's go back so you can be oriented on where we're at. These things right here, these individuals are called the thylakoid, and the stack of them is called the ground. Okay, inside of them, in that space, is a fluid, which is chlorophyll. The fluid that is in the chloroplast itself, out in through here, are called, remember that is the stroma with an R, S-T-R-O-M-A. Stomata are the openings in the leaf. If I can find it again here. So this shows, if we take a small section of that leaf, these are the stomata, the openings. These are the chloroplasts. Inside the chloroplast then are these thylakoids. So that's where we're talking about when you look at this particular one right here. That's showing you that's in the space inside of the thylakoid where chlorophyll is at.
So chlorophyll is the liquid inside the thylakoid.
Right.
Oh, thank you.
Chlorophyll is held contained within the thylakoid. The fluid in the chloroplast itself is called the stroma. So if we look at this system here, light is coming in, going through the leaf, the chloroplast, the thylakoids, where the chlorophyll is at. Okay, now in that thylakoid space is where this reaction center is. We see this is a protein, it's a purpley part, and it's kind of acting like the infrastructure for this to occur, places for it to be. So we've got light hits the chlorophyll, superexcites an electron, which passes it to another chlorophyll molecule and down the line until it comes to these special chlorophyll molecules. Notice they even call them special parachlorophyll molecules. So you'll see what's special about them in a little bit. They have certain other names. They have a specific name, as we will see. But these are just the general chlorophyll molecules, and those general chlorophyll molecules get superexcited and pass their energy then to these special chlorophyll molecules, which then release them, as you see right up through there, to that reaction center. That reaction center has in it what is called the primary electron acceptor. So after the electron is giving up its energy, and then here, these pass the electron that's been excited with all that energy to this reaction center. This is called the primary electron acceptor. First, remember, primary, it's the first electron acceptor. Now that's how the light is captured. Yeah.
You said that the primary electron acceptor would be the reaction center complex? Okay, thank you.
Those chlorophyll molecules are just passing that excited electron down the chain. And then it will be passed to that reaction center where things will start to happen now. what the primary electron acceptor is and does. It says this primary electron acceptor, which is going to be in the reaction center, takes those electrons that have been supercharged or excited by the photon from the sun. They pass the energy to these electrons and gets them to hold a little bit more energy than what they normally will hold. It says solar powered transfer of an electron from a chlorophyll A molecule to the primary electron acceptor is the first step of the light reaction. Two types of photosystems. Remember I told you the last time. Unfortunately, they call the one that comes first photosystem 2. The one that comes second is photosystem 1, so don't get those confused. Photosystem 2 comes first. Notice, this is the important part. Functions first. Those are the numbers reflect the order of discovery, not the order in which they occur. It absorbs a particular wavelength, and that is 680 nanometers. The reaction center chlorophyll of PS2 is called P680. That's the name of that reaction center. It's given a name, P680, referring to the wavelength that it absorbs the best. Photosystem 1, which comes after 2, absorbs best at 700 nanometers. So we've got two reaction centers that absorb at two different wavelengths. During the light reactions, there are two possible ways the electron can move. One is called cyclic, and the other is linear. Linear flow is the primary one. It uses both of those photosystems and produces both ATP and NADPH from the light energy. Now this is kind of a verbal picture walkthrough. It says the photon hits the pigment. Its energy is passed among the pigment molecules until it gets to that P680. This is photosystem 2, first one. Once it gets to the P680, the electron from P680 is transferred to the primary electron acceptor. We call that's in that reaction center, we call it the P680. So here's what happens now in the picture form. We have up here the light that hits these chlorophyll molecules. They're passed down the chain until they get to these two special molecules, which are called P680. And it sends then the electron up to that P680 receptor, primary acceptor. And these, it's occurring on both sides of this. They just show it going from one to one, but it also occurs over here.
When it says an excited electron from P680 is transferred to the primary electron acceptor, we now call it P680 plus. So what are they referring to when they are saying P680 plus?
That's just the name for the identification for the electron acceptor.
Okay, so it's,
The molecules are called P680, the acceptor is 680 plus.
and that's before it receives the electrons, or am I misunderstanding?
The electrons come through chlorophyll to P680 molecules.
Right.
Then it sends the electron to that acceptor, that's P680 plus.
So P680 is a special pair of chlorophyll molecules for the photosynthesis.
They call them P680 photosystem
Okay.
because that's the wavelength. That's where the numbers come
So what was confusing me was that plus sign. So it's
Just an identification up there for that acceptor.
so it doesn't.
You're not talking about the molecule when you say P680 plus, you're talking about the electron acceptor. So, we've got light come in, now there has been energy sent to the primary electron acceptor. Notice here, P680 is a very strong oxidizing agent, which means what? It readily gives up electrons. So now we've got these electrons sent to that reaction center, which its purpose is to give up those electrons of energy. And this is an important point right here. Water is split by enzymes. The electrons are transferred from the hydrogen atoms to P680. Now notice up here, P680 positive refers to the charge of that reaction center. You can identify whether it's talking about which one in this initial stage. The molecules themselves are just P680 that absorb the wavelength. Now the difference with that positive sign, it's indicating a positive charge for the reaction center. So you can designate, are you talking about the reaction center or the molecules by the positive? Now, why? Remember how NAD was called NAD plus? It had the positive charge to it, right? And then when the hydrogen electrons were added to it, instead of being called NAD positive, it was just NADH, right? It picked up an electron. That's the same thing. So you can identify which one they're talking about when you first start photosystem 2. If someone says P680, we're talking about these two little special molecules. When you see P680 positive, it's talking about the reaction center, because now that molecule of the primary acceptor up there, it doesn't tell you what the chemical is. It just says it's a positive charge. It's an oxidizer. When you see the positive, that means it's going to be an oxidizer. So now notice here, strong oxidizing agent, water is split and the electrons transferred from the hydrogen atoms to P680 positive. That will reduce P680 now to, once again, it's just carrying that electron that came from the P680 molecules. Does this make sense? We start from the molecules, which are, just call them neutral, not charged. Okay, they send their electron now to the reaction center that is charged. It picks up that electron, so now it goes back to being the reduced state to just P680.
So P680 is the reduced state, and when it's plus, that's when it has the electron?
That's before it gets the electron.
Right, so then when it gets the electron, it's
It goes
P6.
back to P680.
Okay.
It picks up that, it's no longer charged.
Okay.
See, they don't tell you what P680 is, they're just calling it a reaction center. All the P680 refers to is the wavelength. There is a chemical in that reaction center that's going to be positive, it's going to pick up that electron because it is positive, and now it can move it. Does that make sense?
Yes. So okay, so the P680 plus is a very strong oxidizing agent. It says. So we are talking about the two special molecules.
They are two special chlorophyll molecules designed to carry specifically 680 wavelength, 680 nanometers.
Right.
They pick up the electrons that have been charged. They then give up, they just pass those along. They're not doing it because of different charges or anything. They're just passing it through step by step. The reaction center, however, is charged. It's that positive charge.
Okay. So,
It will pick up that electron and that will bring it back to a neutral state, just 680.
okay. So the primary electron acceptor is P680 plus, and the two special molecules are
Just call them
P680.
P680.
Okay.
That's all it is. You can tell which one is, when you see the positive, you know they're talking the reaction center before it's charged.
So does that P680 indicate like a composition of some sort of chemical or something?
It
And
just
so-
is the wavelength, that's all it is, 680 nanometers. It does not tell you what chemicals make up that reaction center.
It was confused me because NAD, so I know we have NAD plus when we do not have the electron. When we get the electron and it's reduced, it turns into NADH because it's
Right.
losing its positive charge. But
But
this,
this is not a chemical.
okay, so
Remember,
that's,
P680 is not a chemical, it's just referring
it's just
to
the
the
name.
wavelength that the chemical has.
Okay, so it's just the name. Thank you.
Now, the big thing to remember out of here, water is split in this first reaction of the photosystem too. You can also, or almost be guaranteed you'll get that question on the exam. Where is water split? It should be in the light reaction in photosystem two. Notice, the hydrogen atoms, it says the electrons from the hydrogen atoms go to the reaction center, P680, reduce it then to P680 without a charge. Oxygen from that water molecule is released as a byproduct. So, in photosystem two, we have the water molecule being split, the electrons transferred to the reaction center, oxygen is going to then be released. So if you just follow through with this, and it'll start to explain itself a little bit. So look here. This is photosystem two. Light comes in, goes to these electrons. Notice here, water comes in, and we need that hydrogen. So it takes the electrons from that water molecule and sends them to the same two molecules that we use that as extra energy going up to the primary acceptor. The oxygen will be given off with two hydrogens.
And you said that H2O water is split in the light reaction in photosystem 2?
Photosystem two down at the bottom, it tells you down here. So we've got two hydrogens released. We've got oxygen released. It says half of an O2 molecule because H2O, there's only one oxygen. So it will combine with another half oxygen molecule to make the O2 to be released as a gas. Now, notice here, that is an electron transport chain that we looked at, like in cellular respiration. Each electron falls down. We're going to see an electron transport chain with some similar proteins in it that was in cellular respiration. That will lead to photosystem one. So these electrons fall down and electron transport from the primary electron acceptor of 2 to PS1. Energy released by the fall drives the creation of a proton gradient across the thylakoid membrane. Division of hydrogen protons across the membrane drives ATP synthesis. Where did that hydrogen come from?
The
A water molecule that was split. Okay. What happened to the electrons? It went into the primary electron acceptors, P680, and then up to the reaction center, just like the energy came from the sun. We need the hydrogen. Why? Because that's going to be part of the carbohydrate that's made, the sugar at the end, right? So, if you remember the cellular respiration, we had a hydrogen gradient across the mitochondrial membrane that was pulled back down through an enzyme, ATP synthase, in order to make ATP. So now we're making another hydrogen gradient here. Here's the electron transport chain. This is the first one we just looked at. Now add this transport chain. And notice it has similar cytochrome complexes, just like we had in cellular respiration. And also notice here, there is some ATP there. Now, this right here leads to PS1. It's gonna look just like this, but it'll be PS1. In PS1, like PS2, transferred light energy excites P700, a different wavelength, which loses an electron also to an electron acceptor, just as before. P700 positive, that reaction center will be reduced to P700. See, it says the P700 is missing an electron. Accepts an electron passed down from PS2 via the electron transport chain. So here's PS for the photosystem 1. You notice over through here, these electrons that come down the chain go to two special molecules, just like in photosystem 2, except these are P700 instead of P680. The reaction center up here is going to be P700 plus, positive. Electrons will be sent up to that primary acceptor. Also notice, you still have light coming in. All this is taking place in the presence of light. And it is, each of these chlorophylls, these are designed to carry 680 wavelength, and that's the 700.
Sorry, what was the last thing you said? 680, the chlorophyll molecule?
PS2 is 680.
Right.
Photosystem 1, 700. Same thing, it's just a different wavelength, so.
Okay, thank you.
Now, one thing that is different, notice the electrons from photosystem 2 are also going into this while there is light coming in on its own for these molecules. So we're increasing the amount of energy coming into PS1. What was already in the system and now added light to it.
Is that why it's 700 as opposed to 680 in the second one, because it has more energy?
It's not necessarily that it has more energy, but it's the fact it's a different wavelength, and if you capture light energy from different wavelengths, you've got more. If you could only capture it from one, you wouldn't get as much as you can.
Because the shorter has more, because the higher the wavelength.
680 would have more,
Oh,
but still, when you get in that level up there, there's still energy in the 700. So as much as you can capture. And folks, remember something else that happens too. In leaves, we have what is called accessory pigments, right? Different colors that can absorb light in to different wavelengths, so it will come in through here. We say wavelength, P680 and so forth, but they can also be energized from these other pigments, accessory pigments, if it has them. So notice what it says here. Each electron falls down an electron transport chain from the primary electron acceptor of PS1 to a protein, ferredoxin. We've got two electron transport chains along here. One from PS2 to 1, and then one, we'll see where that happens. Just remember it goes to ferredoxin. What does ferra refer to?
Iron.
In Latin, ferric, iron, right. Now, electrons are then transferred to NADP positive. So we've moved these electrons, we've captured from two photosystems. Electrons are moved to that ferredoxin, and now it is going to give those up to NADP positive, which will become NADPH. In other words, NADP positive becomes reduced, picks up the electron. What happens then? The electrons of NADPH are available for the reactions of the Calvin cycle. process also removes the hydrogen proton from the strontium. Let's look at the pictures. Photosystem 2, we've covered photosystem 1. So once these go up to the photosystem 1 electron primary acceptor, it passes those electrons to paradoxin, and the little transport chain here is an enzyme, NADP positive reductase. What do you think that reductase means?
It's accepting
It's
the.
going to reduce something. It's going to take that electron and reduce NADP positive.
Oh.
Enzymes are usually named after what they do. Not always, but usually. This is telling you it's going to reduce NADP with that electron that came from paradox. And I say that electron. This is going quickly. There's a lot more than just the one electron, obviously, but they're past two NADPHs positive. So now we have got reduced NADPH at the end, and we did make some ATP. That ATP can fuel reactions within the league normal things. Energy, it needs energy too, right? And this is showing you basically what's happening. Remember we said, what is the benefit of an electron transport chain? Not to release all of the energy at once in an explosive manner, because it would do damage to these systems. These tissues and things they're talking about are very, very easily delicate. They're very easily to disrupt. Shows the worker here being the energy source, the photon source, putting the electron up, going down the chains, and so forth. That was linear. Now let's look at cycling. One of the things about photosynthesis it tries to do is to be very efficient. Cyclic electron flow uses only photosystem 1 and produces ATP, but not NADPH. No oxygen is released. Cyclic electron flow generates surplus extra ATP, satisfying the higher demand that's going to be in the Calvin cycle. Remember, Calvin cycle is going to be making sugar and carbohydrates. It's going to take a lot of energy. So every place that can occur, it wants to get all the energy it can. Notice right here, light is still coming in, right? Only in photosystem 1. But it's not using this water and the hydrogen. It's only got light coming in, and then it's going into this cyclic flow up and through here to create energy, ATP, but it does not create NADPH. What would be a good reason for it not to create NADPH? Where does the hydrogen come from? It doesn't split a water molecule. So now it's just using the energy to make energy to send to the Calvin cycle. So that photosystem 1 does two jobs. It cycles in a linear fashion the electrons that came out of photosystem 2, and it also accepts more light coming in and goes through the cyclic to create ATP. Kind of think of it this way. If we had this big old photosystem here, and the only thing it did was just take electrons from there and do nothing else, it would miss its opportunity with all these chlorophyll molecules to pick up other energy it could take. Now it doesn't have the hydrogen to make NADPH, but it's got energy that it can phosphorylate ADP and make ATP. So it's a second source of energy. And this kind of shows this flow here. We've got light that comes in. Notice. Runs runs it right up to that primary electron acceptor. So it's just an other way to capture some of the energy from that sun. Notice some organisms, such as purple sulfur bacteria, these are bacteria that can metabolize sulfur and get the energy from it. They only have PS1, but not PS2. Why? Because they don't have to have oxygen and the water molecule split going on. They don't have photosystem 2, but they can still get energy from that cyclic flow. And notice, this may be a way of absorbing some of the energy so it all doesn't go into one place and cause a problem, damage to the tissues. Maybe. Nobody don't really know that. That's a possibility. Now, the way, the term, whenever we took ADP in the electron transport chain and used the energy given off by NADH, the electrons and the proton gradient, the electron transport chain separated the electrons and made the gradient. Whenever the hydrogen will pull down through the enzyme to make a force to make ATP out of ADP, that was called chemiosmosis. Osmosis going through chemi refers to that positive negative attraction. Okay. Here it says chloroplast and mitochondria generate ATP by chemiosmosis, but use different sources of energy. Mitochondria use the energy that comes from a food molecule, broken down. Chloroplasts use it from photons from the sun to capture it, and then the chlorophyll transfers. Mitochondria transfers chemical energy from food to ATP. Chloroplast transforms light into chemical energy of ATP. Spatial organization of chemiosmosis differs between chloroplast and mitochondria, but it also is similar in many ways. Mitochondria protons are pumped to the membrane surface and drive ATP synthesis as they come back through the membrane. In chloroplast, protons are pumped onto the thylakoid space, or into it, onto it, and drive ATP synthesis as they diffuse back into the stroma, the fluid. That is where? In the chloroplast. So there's similarities but differences. If you notice right here, your electron transport chain, hydrogens go through ATP synthase and make ATP. The big difference is, where does that energy things come from? In a mitochondria, it's occurring on that inner membrane, right? Up here. That's the membrane. In the chloroplast, it's whenever it leaves the thylakoid and goes back into the stroma. In other words, it has to be pulled out of the inner space of the thylakoid membrane back into the stroma. And then we've got ATP made. ATP and NADPH are produced on the side facing the stroma, where the Calvin cycle will take place. In summary, light reactions generate ATP and increase the potential energy of electrons by moving them from water to NADPH. This shows the thylakoid space in the membrane right there. That kind of gives you a total summary of photosynthesis. See photosystem 2, photosystem 1, NADPH is being made, and look where it goes to, Calvin cycle. But
Did we name PQ or PC on the electron transport chain there?
no,
Okay, just FD.
That is just the name of the proteins that cause it. Don't worry about it.
Okay.
But notice it's these hydrogens come back through ATP synthase. ATP synthase, this is the thylakoid. Pulls it through across the membrane back into the stroma, making ATP using the same kind of enzyme, the ATP synthase, as we use to break it down when we go through cellular respiration. So the process is really similar to cellular respiration. It's the reverse, or more or less. Now the Calvin cycle. Remember, coming out of the photosynthetic light reaction will be ATP that will go to the Calvin cycle. It will also bring in NADPH. Two forms of energy. NADPH, remember, is made after we go through the second electron transport chain of photosystem 1. We've got hydrogen, remember, that was released, right? When the water molecules split. So we've got that hydrogen that will then make a gradient. It's on this side of the membrane. And then there's a low hydrogen concentration here. So it goes from this high concentration to the low through that membrane, driving phosphorylation and making ATP. What do you think? Now, where is that hydrogen located now? After it comes through ATP synthesis.
In the
Stroma.
In the stroma, right? Where does carbon fixation take place? Stroma. What does we need to make a sugar? Carbon dioxide and a hydrogen. So we use that hydrogen to come through across that membrane again to make ATP. Now that's on the other side, it's available to make sugar out of it. Okay? This is just showing you where does the hydrogen to make carbon fixation come from. Came from that water molecule. Now it's going out into the stroma. This is where carbon fixation or the Calvin cycle takes place. So now we placed hydrogen there. The Calvin cycle uses the chemical energy of ATP and NADPH to reduce carbon dioxide. What's going to be reduced about it? Are we going to add to it? Hydrogen. That will make sugar. The Calvin cycle, like the citric acid cycle, regenerates its starting material after molecules leave the cycle. Where's the electron from that hydrogen at? We can carry it by NADPH, right? And then we got the protons down there. So we can reunite those into just a regular hydrogen molecule that will be placed with that carbon dioxide to make sugar. The Calvin cycle, like the citric acid cycle, regenerates its starting material. Remember, in the citric acid cycle, it was oxaloacetate combining with the acyl group to make citric acid. Similar happens here. The cycle builds sugar. And remember, that form of sugar is CH2O. It does it by using the energy from ATP and the reducing power of that hydrogen electron on NADPH. Here's something you saw in the cellular respiration cycle, right? We were starting to break down sugar, and one of the stages there in that fifth step was G3P. Carbon enters the cycle as carbon dioxide. How does carbon dioxide get to the leaf? the stomata. They open up and will let carbon dioxide come in. How does oxygen escape the leaf? Same way. The stomata lets oxygen out, carbon dioxide in when it's needed. When does carbon dioxide come in to photosynthesis? What stage? The dark reaction of the Calvin cycle.
Just to get it clear, do plant cells not have mitochondria?
Plant cells go through and,
I could have sworn they did.
they have to go through cellular respiration stuff too. They have to have energy
Or if the chloroplasts take the place of mitochondria in an animal
for
cell.
this purpose, yeah. For this purpose. Mitochondria acts, it provides the membrane and the spaces and resources to break down the product of the chloroplast.
Yeah. So it doesn't do the same function as it does in our cells.
Yeah. Well, sort of, but
Similar,
there, yeah,
not exact.
right. Carbon, if you go back and look, one of the things it said, there's the thing we talked about, the endosymbiont theory of mitochondria. It's how we got mitochondria from bacteria, same way chloroplasts developed in the plant. So G3P, glyceraldehyde 3-phosphate is the chemical. Instead of breaking glucose down to getting to G3P, now we're taking G3P and building up to make glucose. For net synthesis of one G3P, the cycle must take place 3 times, fixing 3 molecules of carbon dioxide. The Calvin cycle has 3 phases, 3 parts to it. Carbon fixation, which is going to be catalyzed by this enzyme rubisco reduction, which means what? Adding an electron. Then regeneration of this CO2 acceptor, RUBP. Ribulose is phosphate. That is regenerated, just as oxaloacetate was regenerated. Now, I'm not making you remember all these chemicals and things in here. There are a few things I do want you to remember about it. Rubisco is going to, as it says, catalyze this carbon fixation, this enzyme rubisco. It's going to catalyze. We've got 3 carbon dioxides coming in. They're going to be added to right here. We are going to get all of these things, and it's going to just same as in the citric acid cycle. We start this time, instead of this cycle, carbon fixation giving off energy, it is now going to be using it. And it will then use that energy. If you notice, energy comes in, so this 3-phosphoglycerate right here is going to become 6,1,3-bisphosphate. We've got NADPH coming in, that extra energy. Notice here, 2 phosphates, now we're down to 1. Glyceraldehyde 3-phosphate, and the outcome is going to be this sugar eventually. That G3P will be used to make the sugar, carrying energy.
So we can only get one G3P molecule after 3 turns.
Out of 3 carbon dioxide, right? You have to go through the cycle 3 times. And that G3P then will fuel the making of the sugar. But look what happens also. That 3GP or G3P keeps going on the system, that's the way we get the ribulose biphosphate. We'll pick that up, go through that again next time, but that base setup.
So you wanted us to remember that Rubisco is the enzyme. Wait, it's an enzyme,
Nabisco,
and it catalyzes the reaction between ribulose bisphosphate and CO2.
power,
Power.
making that sugar.
And then that makes the short-lived intermediate.
What?
Sorry, that makes the short-lived intermediate.